This is Chapter 6, Angular Kinematics. Here's a list of objectives for this chapter, including learning about absolute angular position, looking at angular position, displacement, velocity, and acceleration, talking about tangential acceleration and centripetal acceleration, and really looking at the relationship between average linear speed and average angular velocity. The term angle refers to the orientation of lines or planes to each other. So an angle is therefore formed by the intersection of two lines or two planes or a line in a plane. Angular position refers to the orientation of a line or plane with another line or plane. If the other line or plane is fixed and movable relative to Earth, then the angular position is considered to be an absolute angular position. If the other line or plane is capable of moving, the angular position is relative angular position. An example of this would be the angle of the knee. If it's in flexion or extension, those two segments, the upper leg and the lower leg, or the thigh and the shank, make up the relative angular position. The radian, which is a unit of measure for an angle, is really a ratio of arc length divided by the radius. If you recall, the circumference of a circle is 2 pi r, so there are 2 pi radian in 360 degrees, or 57.3 degrees in 1 radian. Let's talk briefly about the right hand thumb rule as far as understanding how to determine the direction of rotation and whether it's positive or negative. I'm going to see if I can make this video play here. And yep, I can. Perhaps. Okay.
Good morning. Today is the day. We have avoided it long enough. Today we define angular directions. Oh, good. Okay. Flippin' physics. Yay. We are going to use the right-hand rule to define the directions of angular velocity and angular displacement. The first impediment which prevents students from being able to correctly implement the right-hand rule is finding your right hand. So please, hold up your right hand. The second impediment to being able to successfully implement the right-hand rule is that some of my students think they are too cool for the right-hand rule. For some reason, students feel they are too cool to actually turn their shoulders and torso while performing the right-hand rule. So please observe how cool I am while I perform the right-hand rule without moving my shoulders or torso.
That is definitely not cool. I know cool.
That is definitely too cool. In order to not be too cool for the right-hand rule, please limber up. What? Limber up, people. Stretch. Okay, now that we have found our right hand and we are limber, let's do our first example. Here is a mint revolving on a turntable. The mint is revolving in a circle, and I have added arrows to the circle to indicate the direction the mint is moving along that circle. Now, everybody take your right hand and point your fingers along the arrows on the circle through which the mint is moving. Please, now everybody has to do this, including you, the person watching this video. Again, curl the fingers of your right hand to make them follow the circle through which the mint is moving. And then stick out your thumb. Your thumb is pointing in the direction of the angular velocity and angular displacement of the mint and of the turntable. Notice, everybody's thumb is pointed out of the screen. In other words, this mint and turntable have an angular velocity and an angular displacement which are both directed out of the screen.
Wow,
Okay. That's pretty cool. Good. Now let's do another example. Again, we have the mint revolving on the turntable, only the direction has changed. Again, I have added arrows to the circle to indicate how the mint is moving along that circle. Please take your right hand and point your fingers along the arrows on the circle through which the mint is moving. And curl your fingers to make them follow the circle through which the mint is moving, and then stick out your thumb. your thumb is pointing in the direction of the angular velocity and angular displacement of the mint and turntable. Notice everybody's thumb is pointed into the screen. In other words, this mint and turntable have an angular velocity and an angular displacement which are both directed into the screen.
Mr. P, why don't we just use clockwise and counterclockwise? I think that would be easier.
Yes, okay. So, looking at this example, Billy, you as the observer, would you say this mint is revolving in the counterclockwise or the clockwise direction?
That looks clockwise to me.
Right, but to me, someone who is on the other side of the turntable, the mint appears to be revolving in a counterclockwise direction. So, who is correct? Is it revolving clockwise or counterclockwise?
We are both correct. It just depends where the person is standing who is describing the angular direction.
Correct. Clockwise and counterclockwise are observer-dependent directions. For physics, we need angular directions that are not observer-dependent, which is why we use the right-hand rule. Notice how no matter where you, the observer, are located for this example, using the right-hand rule, you get that the turntable is turning into the screen. Let's do another example. Now we are looking at the turntable from the side. Again, use the right-hand rule. Curl the fingers of your right hand in the direction the turntable is rotating, and class, which direction do we get?
Up.
Correct. You can see the mint and turntable have an upward angular direction, which is also the positive y direction. Okay, let's change that direction again. Bo, this time, what is the angular direction of the mint and turntable?
My thumb points downward, so looks like the mint is turning downward, so the negative y direction.
That is correct. The mint and turntable are rotating in a downward direction, which is the negative y direction. Now let's turn the turntable on its side. And Billy, what is the angular direction now?
It looks like it's going in this direction, which is the positive x direction.
That is correct. And now let's do our last direction. Bobby, please.
I think it's going this way, which is the negative x direction.
Also correct. Very nice, everybody. Now, I do want to remind everybody that the right-hand rule gives the direction of the angular displacement and angular velocity of the turning object. One last thing which can be confusing for students. The direction of the angular displacement and angular velocity of a turning object is normal to the plane in which the object is located. Let me say that again and illustrate it. This turntable is located on a horizontal plane. In other words, a plane which is parallel to the ground. And the turntable has an angular velocity which is, according to the right-hand rule, directed upwards, and up is at a 90-degree angle or normal to the horizontal plane, which is why the direction given by the right-hand rule is normal to the plane in which the object is located. Thank you very much for learning with me today. I enjoyed learning with you.
Okay, I hope that that video is helpful in understanding why the right-hand thumb rule is used and as a way to ensure that everybody is identifying a positive or negative direction, something that should not be based off of just where you're standing or where your perspective is, but something that is that's static, that's going to remain no matter where you're at. Angular displacement is the angular analog of linear displacement. It is the change in absolute angular position experienced by a rotating line. It's the angle formed between the final position and initial position of a rotating line. Angular displacement has direction associated with it. Clockwise and counterwise are the most common terms used to describe the direction of rotation. It's important to identify the axis of rotation and the plane in which the parts move in order to eliminate confusion about the direction of rotation. The axis of rotation is always perpendicular to the plane in which the motion occurs. Thus, that's why he was talking about it's normal to the plane, creates a 90-degree angle. The image above shows the angular displacement of a pitcher's arm at the shoulder joint around the anterior-posterior axis. In order to determine the displacement, we need to know the initial and final position of the arm, as demonstrated by the angular displacement formula, which is the change in theta is equal to theta final minus theta initial. The initial starting position is at 5 degrees abduction. He then moves his arm through an abduction as much as possible until he reaches 170 degrees. Therefore, the angular displacement is 170 degrees minus 5 degrees equals a positive 165 degrees. Whenever there's a small moment arm, the muscles have to produce a large amount of force in order to create modest torques and thus movement. In this case, it may be said that the muscles are at a mechanical disadvantage. However, is there any advantage to this type of arrangement, where the muscles are attached closer to the joint? To consider this, try placing your forearm on a desk or a table in front of you. Flex at the elbow and bring your hand off the table, moving it toward your shoulder as far as possible while keeping your elbow on the table. You might notice that all the parts of the arm underwent the same angular displacement, but which moved farther, your hand or the point of the attachment on your biceps muscle? We can tell that your hand moved the furthest, right? The linear distance it traveled and the linear distance or linear displacement are larger than the linear distance and linear displacement traveled by the biceps insertion. How far any point on the arm moves when you flex your arm is dependent on how far that point is from the elbow. This relationship is actually apparent in the definition of an angle measured in radians. So the change in theta is equal to the length or arc length divided by the radius. For this example, we will use angular displacement measured in radians. So again, the arc length of A divided by the arc length of B, or the radius of A divided by the radius of B. If the angular displacement of the arm was 1 radian, RA was 10 inches and RB was 1 inches, then LB, or LB and LA, divided by each other, so 1 inch divided by 10 inches is going to equal 1 inch. In this example, the hand moves 10 times as far as the insertion of the biceps tendon. The linear distance, or the arc length, traveled by a point on a rotating object is directly proportional to the angular displacement of the object and the radius, the distance that point is from the axis of rotation of the object. Angular velocity is defined as the rate of change of angular displacement. So just like if we're talking about speed, if we're just talking about linear velocity, it's the same formula, except now we're just considering rotation. Average angular velocity is computed as omega is equal to the change in theta divided by the change in time. So if we are concerned with how long it takes something to rotate through a certain angular displacement, average angular velocity is the important measure. When we are concerned with how fast something is rotating at a specific instant in time, instantaneous angular velocity is the important measure. The relationship between angular displacement and linear distance traveled provides the answer. Let's consider a swinging golf club. All points on the club undergo the same angular displacement and thus the same average angular velocity because they all take the same time to undergo that displacement. But a point on the club closer to the club head or farther from the axis of rotation moves through a larger or a longer arc length than a point further from the club head or closer to the axis of rotation. The 2 points travel their respective arc lengths in the same time. The point farther from the axis of rotation must have a faster linear speed because it moves a longer distance but in the same amount of time. Mathematically, this relationship can be derived from the relationship between angular displacement and linear displacement traveled. So the length is equal to the change in theta times radius. Dividing both sides by the time it takes to rotate through the displacement gives us our average linear speed is equal to our average angular velocity of the rotating body times the radius of rotation for that point. Thus, the average linear speed of a point on a rotating object is equal to the average angular velocity of the object times the radius, or the distance from the point of the object to the axis of rotation of the object. Let's do practice here. So here's the problem, okay? Consider two baseballs that are consecutively hit by a bat. The first ball is hit 20 centimeters from the bat's axis of rotation, and the second ball is hit 40 centimeters from the bat's axis of rotation. If the angular velocity was 30 radians per second at the instant that both balls were contacted, what was the linear velocity of the bat at the two contact points? Using the formula that relates linear and angular velocities, we see that the linear velocity for ball 1 is 6 meters per second, and for ball 2 is 12 meters per second. So we see that impact there of where the ball made contact with the bat based on that distance from the axis of rotation. It definitely changed that velocity, that linear velocity of the ball. The sticks, clubs, and rackets that are used in sports mentioned at the beginning of this chapter all use the relationship between linear and velocity and radius. The linear velocity of a point farther from the axis of rotation is faster if the angular velocity is the same. The woods, which is the longest club in a golf bag, they're used for imparting a faster velocity to a ball to make it travel farther, whereas the shorter clubs are used for closer shots. The relationship among linear and angular velocities and radius of rotation also explains another advantage of the insertion of our muscles close to the joints. Consider the insertion of the biceps on the radial tuberosity. If it inserts only 1 inch from the elbow joint and the hand is 10 inches from the joint, when the arm rotates, the linear velocity of the hand will be 10 times as fast as the linear velocity of the biceps tendon. Because the velocity of the muscle contraction is limited, the insertion of muscles close to the joint allows a relatively slow contraction velocity of the muscles that will actually be amplified at the end of the limb. Let's talk about angular and tangential acceleration. Angular acceleration is the rate of change of angular velocity. It is computed as the angular acceleration is equal to the change in omega divided by the change in time. Angular acceleration occurs when something spins faster and faster or slower and slower. Just like linear acceleration, right? If something's speeding up, it's a positive acceleration. If something's slowing down, it's a negative acceleration. It can also occur when the spinning object's axis of spin changes direction. The component of linear acceleration tangent to the circular path of a point on a rotating object is called tangential acceleration. Essentially, a line is tangent to a circle if the line intersects the circle at just one point. A line from this point to the center of the circle, also known as the radial line, is perpendicular to the tangent line. A point on a rotating object undergoes linear acceleration tangent to its rotational path and equal to the angular acceleration of the object times the radius. So just to kind of give you an example of what tangential acceleration looks like in motion, I want you to watch as this squirrel spins around and then as the squirrel flies off in this straight line or tangential to the circular path that it's traveling. This is like a real squirrel, this is really funny. I'm watching, he's gonna let go soon.
That's the best one I've ever seen.
You saw how he kind of let go, and that line that was created from where he let go, that's that straight line or that tangential acceleration that occurred because of the angular acceleration. And there's also centripetal acceleration occurring in that video as well. So centripetal acceleration is the linear acceleration that's directed toward the axis of rotation. Linear acceleration occurs if something speeds up, slows down, or changes direction. A point on an object spinning at a constant angular velocity doesn't speed up or slow down, but because the point follows the circular path, it is constantly changing direction, thus experiencing a constant linear acceleration. In order to better understand the concept, think about a weight tied tightly to a string. And if you were to spin it around so that it circles with a constant angular velocity, you would kind of be able to kind of see, how do you have to pull, which way do you have to pull on the string in order to keep that weight traveling in a circle. And you'd probably notice that you have to pull it toward you or toward the inner part of the circle. If you pull on the string with a force directed towards the center of the circle or toward the axis of rotation, and if that angular velocity is held constant, then centripetal acceleration is directly proportional to the radius or rotation. If the tangential linear velocity is held constant, then centripetal acceleration is inversely proportional to the radius of rotation. Another example where we would probably see centripetal acceleration is running around a track where we have, if you're running around a curve on the inside lane of a running track, you experience more centripetal acceleration and thus require more friction on your shoes to exert centripetal force on yourself than you would if you ran the same linear speed in the outside lane. In both of these cases, tangential linear velocity would be the same, but the radius of rotation would be larger in the outside lane, thus a smaller centripetal acceleration. Another reason why races like the 200 meters is started with this person in the outside lane up ahead, staggered. It's a staggered start because this person out here not only is going to experience less centripetal acceleration, but also is technically going to run a little bit longer of a distance. Okay, we're going to move on to talking about anatomical planes now. The sagittal plane, which is also known as the anterior-posterior plane, is the plane that runs anterior or front to posterior. So it runs front to back and superior, top to bottom, dividing the body into right and left parts. So this is if we were to take your body and we were going to draw a line right down the center in between your eyes, down your nose, down the rest of your body. That is giving us an idea of what that sagittal plane looks like. The frontal plane or the coronal or lateral plane runs side to side and superior to inferior, dividing the body into anterior and posterior parts. And the transverse plane, also known as the horizontal plane, runs from side to side and anterior to posterior. So it divides the body into superior and inferior parts, so top and bottom. All sagittal planes are perpendicular to all frontal planes, which are perpendicular to all transverse planes. So every plane rotates about an axis, okay? And there are three anatomical axes: the anterior-posterior axis, or also known as the sagittal axis, which runs anterior to posterior, and it's perpendicular to the frontal plane. So that's an important piece here. The transverse or lateral, frontal, medial lateral axis runs from left to right and is perpendicular to the sagittal plane. So if the axis is perpendicular to the plane, then that means that that plane is rotating about that axis. And you can tell here that there are several different names for each of these. I just find that you need to pick whatever you're comfortable with. I've gone with anterior, posterior, medial, lateral, and longitudinal for years because that's how it makes sense in my mind. The last one is the longitudinal, which is also the vertical axis, and it runs from top to bottom and is perpendicular to the transverse axis. So you see table 6.1 there. It says anatomical planes of motion and their corresponding axes of motion. So if I ask you about, in which plane does running occur in? Well, primarily that's occurring in the sagittal plane, And then the second part of the question might be, and which plane and axis does running occur in? Well, since we know that the plane is sagittal and that the axis that it rotates about is going to be perpendicular, then that tells us it's going to be the transverse or the mediolateral plane, or sorry, axis. I would spend some time, if I were you, just looking at the pictures and understanding some of the anatomical position, which right now, with her arms down beside her, this is considered anatomical position. And it's important to assume that, because if you don't assume anatomical position, then when you try to determine what is happening position-wise, you're not going to be referencing from the correct position. So these are images of shoulder abduction, right? AB moving away from the body, from the sagittal, frontal, and transverse planes, as well as movement of the shoulder along the longitudinal axis. But I would just spend some time actually doing these motions and understanding what they're called, how they should be referenced. Sagittal plane joint motions at the wrist, elbow, and shoulder are occurring here. So we see flexion right here when you are folding your palm. Flexion here when you lift your arm at the elbow. Okay, hyperextension of the shoulder. This sagittal plane joint actions at the knee, hip, trunk, neck, and ankle. So sagittal plane is when motions in the sagittal plane are going to be flexion and extension primarily. These are images of frontal plane joint actions at the shoulder, hip, wrist, ankle, trunk, and neck. So this would be like lateral trunk flexion, abduction, adduction, things that move away or close to the medial line. And then transverse plane joint actions at the hip, shoulder, radial ulnar joint, and neck joint. A lot of rotation that you see there. So when rotation is occurring, or horizontal abduction or adduction, we know that that's occurring in the transverse plane. And then just to kind of break it down, this is kind of a good table to look at as well, the joint actions and their corresponding planes and axes of motions. So I mentioned earlier that sagittal plane motions are usually flexion, extension. We also see hyperextension, plantar flexion, dorsiflexion. The frontal plane there, we have abduction, adduction, deviations, inversion, eversion, elevation, depression, rotation, lateral flexion. Transverse plane, we see internal rotation, external rotation, pronation, supination, horizontal abduction, horizontal adduction, rotation to the right and rotation to the left. So again, I just recommend spending some time actually doing these movements and talking yourself through which plane that movement is occurring in, and then which axis is rotating around, or what plane the axis is perpendicular to. All right, that wraps up chapter 6.